Hi there, I'm Dr. McFerrin with DM Explains. In this video, I'm going to give you some basics for building up the concept of using state space control. So first, let's assume that you know how to get a state space model. If you don't, I would highly recommend that you check the link in the upper corner, which links you to the beginning of my series about how to get state space models. So a state space model looks like this. I've got x dot of t is equal to a x of t plus b u of t. Sometimes I use r of t here to point out that it is the reference input, but u of t is the traditional thing that you should use. And then y of t, the output equation, is equal to c x of t plus d u of t. So the top equation is what I call the state equation, and the bottom equation is what I call the output equation. X of t is a vector of length n as in Nancy. N is the number of states, also called the system order. Y of t is the output, and it is the vector of length m. And m is the number of sensors or outputs. U of t is a vector of length r, and r is the number of inputs. And doing a little bit of simple math then, that means that A is a matrix and it belongs to the real numbers n by n. So that means that the numbers within the matrix will be real and the dimensions of the matrix will be n by n. B is belonging to the real n by r. C belongs to the real numbers m by n. And D belongs to the real numbers, and it's m by r. One assumption that we're going to make for the purpose of this video as an introduction to state space control is that we have linear, time invariant, causal systems. State space can be generalized to nonlinear, time-varying systems, but for the purpose of this video, let's assume that we have linear, time-invariant, causal dynamic systems. The solution to the state equations is x of t is equal to x 0 input of t plus x 0 state of t. This is mirrored very closely with the differential equation understanding that you would get early on in a control systems course. So the 0 input response is when the input is equal to 0. The 0 state response is when the initial conditions are equal to 0. So x 0 input of t is equal to e to the a t x of 0. I'm going to box that and then give you some further explanation. So e to the at is what I call the matrix exponential. The matrix exponential is not the same as taking e to the a matrix times t. That is not equal to that. Let's actually do a little bit of math to figure out how to get the matrix exponential. So let's figure out what it actually is. So let's let u be equal to 0. This is the condition for x 0 input. If that's true, x dot is equal to a times x. So now what I want to do is take the Laplace transform. So if I write out the Laplace transform, we assume there are some initial conditions. So for this derivative, I've got s x of s minus x naught, the initial condition, is equal to a x of s. So let's isolate x of 0 to one side and get the x of s's gathered together. I've got s x of s minus a x of s is equal to x of 0. So because s and a are pre-multiplying x of s, I'll pull out a pre-multiplier, s times the identity matrix minus a times x of s is equal to x of 0. And then if I want to isolate x of s to find my state, I'm going to take the inverse of si minus a and pre-multiply it, si minus a, and I'll pre-multiply it on both sides, si minus a, inverse x of 0. If I take any matrix and multiply it by its inverse, I get the identity matrix, and the identity matrix times a vector is just the same as that vector. So I'm left with x of s is equal to the si minus a inverse x of 0. And so to get x of t, and in particular 0 input of t, I need to take the inverse Laplace transform. So it's the inverse Laplace transform of si minus a inverse times x of 0. And so that means that e to the at is equal to the inverse Laplace transform of si minus a inverse. So that's the 0 input response. Let's look at the 0 state response. x0 state of t is equal to e to the at b u of t. In other words, x0 state of t is equal to the inverse Laplace transform of si minus a inverse times b u of t. I don't want to do the whole proof here, but it is worth stating the value. Doing all of these proofs in detail is much more like graduate level control systems, and I'm trying to just provide an introduction. Y of t, the output equation, says that cx of t plus du of t is equal to y of t. I know that x of t is equal to e to the at x of 0 plus e to the at times b u of t. So if I plug that into the output equation, y of t is equal to c e to the at x of 0 plus b u of t plus d u of t. So if I want the time domain value for y of t, I'll get it by doing this. For a system transfer function, which is what we typically use in control systems, at least for the purposes of general classical controls. So for a system transfer function, there's a couple conditions. The first is that initial conditions are 0, which means that x of 0 is equal to 0. So y of s is c times si minus a inverse b plus d times u of s. And so y over u, the overall transfer function, is just c times si minus a inverse b plus d. One important note while I'm here is that the si minus a inverse has the determinant of si minus a as the denominator. That is important because as you do classical controls, you learn a whole lot about the poles determining things like stability and so on. In fact, the determinant of si minus a is the characteristic equation. The roots of that determinant are, in fact, the system poles, also called the eigenvalues. From these, we know about stability. The eigenvalues, if they're all negative real parts, then I know for sure the system is stable. We also know the response characteristics because we can find zeta, omega n, other information about the damping and response. And if we know this, maybe what this means is that we can come up with some sort of control law which allows us to get a response that we want. And of course we can, but the caveat is that the system has to be controllable. The system must be controllable for this to work. Okay, so the rest of this video is going to be spent talking about controllability, and then in the next video I'm going to talk about how we'll actually design a controller. So the example I have for you of controllability is, imagine this beam which is suspended by springs, or I guess in this case held up by springs. Let's say the center of mass is right there, and I've got theta of t here. I've got an input that I can actuate on that u of t, and then I've got a position x of t, and let's say each of the springs have an equal spring constant k. So the placement of the control actuation on this system at the center of the beam means that I can control one of the two possible states, theta or x. In fact, I can control just x. I can control x, the vertical displacement, but not the rotation theta. So that means in this case, theta is an uncontrollable state. The reason I bring this up is so that way you get a feel for what I mean by a state that we just can't control. By the placement of the actuator at the center of the beam, there is no way on earth that I can control theta. I could move the control actuation, but it may have other consequences. For example, the relationship between the input and the displacement may then not be easily controllable, or may have very complicated dynamics. So to get us through this, what I need to do is give you a definition, and I'm going to skip any sort of proof of it because, like I said earlier, this is sort of an introduction to state space control topics. So a linear, or an LTIC system, is controllable if for every state x star and time big T greater than 0, there exists a control actuation u of t for all time between 0 and big T, such that the state is transferred from x of 0, the initial condition, to x at big T equal to x star. Okay, that's a lot of words, and all those words mean is that if I have a desired state in a finite amount of time, I can use a controller to take my system from its initial condition to that final state. The mathy way of writing this is, for all x star t greater than 0, there exists u of t such that for all t in the range from 0 to big T, such that x of 0 goes to x star, which is equal to x at big T. That's the very mathy, wordy definition, but how do I deal with this in practice? Well, to determine if a system is controllable, I start by constructing the controllability matrix, which is going to be C. It's sort of a scripty C, and scripty C is equal to B, AB, all the way to A to the n minus 1, n being the number of states, times B. What this means is that C is a matrix that is in the set of real numbers that are n by in R. Then the system is controllable if the rank of C is equal to n. In other words, the system is controllable if there are exactly n, the number of states, linearly independent rows or columns. In MATLAB, I type rank of the CTRB of A, B. You could go ahead and check that out. Let's try it with A equals 0, 1, -2, -6, and B equals to 0, 1. I'm going to do it quickly by hand, but then we'll also do it in MATLAB. So for this one, the controllability matrix is first B, so 0, 1, and then it's equal to A times B, so that would be the multiplication of 0, 1, -2, -6 with 0, 1, so that's equal to 1, -6. So to check the number of linearly independent rows and columns, or the rank of the system, I see, is there anything that I could multiply this first column by to get the second column? The answer is no. So the rank of this controllability matrix is 2. Let's try one more. Let's say A is equal to 1, 2, 2, 4, and B is equal to 0, 1. Then the controllability matrix is going to equal to 0, 1, and then it's going to equal to 2, 4. And again, there's absolutely nothing that I can do to multiply this first column, so the rank of C is equal to 2. Now that I've discussed controllability, let's go try these in MATLAB and wrap it up from there. Okay, so what I would like to do is test those two examples here. So let's make A equal to 0, 1, -2, -6, and have B be equal to 0, 1. Then I need to construct the controllability matrix. I just want to check that what I have is correct. So CTRB of A and B should be 0, 1, 1, -6. And if I want to check the controllability, I will just use the rank of CTRB of A, B. Check the rank is 2. That means that the system is controllable because the rank is equal to n. Let's repeat this with a changed A. A is 1, 2, and 2, 4. B is going to stay the same. Let's check my controllability matrix. I've got 0, 1, and 2, 4. And if I check the rank of that, I get a rank of 2, just like I did by hand. So with all of this in mind, if a system is controllable, we can design state space controllers for full state feedback. The method we will use is what's called pole placement, and it allows us to put the poles where we want. And that's the subject of my next video, which I hope you will tune into. That's all I have for this video. Thanks for watching.